Thank you very much. Good afternoon, everybody. I'm going to talk about natural treatment systems. We worked on this for several years, back when I was at Democritus University of Thrace, and together with various colleagues, Dr. Gikas, Dr. Moutsopoulos, various students, Dr. Akratos, he's back there, Ms. Koti, who is at the Secretariat in front, and Dr. Stefanakis, Dr. Liolios, he's back there, and so on. So all what I'm going to present is the results of several years of studies together with my colleagues. I'm going to present a short introduction on the natural treatment systems, and particularly constructed wetlands, and some comparison with conventional wastewater treatment systems, examples from EU applications, data we collected over the years throughout experiments and monitoring of these systems, and system design, system cost, and some conclusions. So the legislation that guides all this is Directive 271 from 1991, which obliges all EU countries to provide suitable treatment facilities for their settlements. And the limit is settlements of more than 2,000 people. As Dr. Vassilios said, in Greece we have treatment for at least 85% of the population, but only 30% of the needed facilities have been constructed and are in operation. And we see this in these two graphs. To the left, we see the number of wastewater treatment plants, and you see the ones that are needed. There are about 460 or 470 treatment plants that need to be constructed. Only about 150 or 33% are in operation today. So there is a lot to be constructed yet. In terms of population served, we see the right graph here, which shows that the needs are for about 12.5 million population equivalent, but already about 10.5 million are served, so 85% or more. And this, what this shows is that the population that's served is from the large urban centers. So the large urban centers have their facilities, but what is left is the small settlements, the small villages. All these are not served, and they will require facilities. And this is also shown in these graphs here. The top two graphs show the needs for small facilities between 2,000 and 10,000 people. 76% are the needs, 76%, and in terms of population equivalent, 11% of the population, and in operation are about 41% or 3% in terms of population. So all this brings us to these natural treatment systems, which we believe are appropriate for the small settlements, and particularly in rural areas where there is a lot of land, and probably also public land, which will be made available for these systems. And another thing is that the conventional wastewater treatment facilities have various problems, at least in Greece, but I believe in other countries also. And these are operational problems. So, for example, they don't provide the treatment efficiencies. They have a high operational cost, that's electricity and chemicals, and also there is lack of personnel. So what are our natural treatment systems? They use various physical, chemical, and biological processes when they occur when wastewater comes into contact with soils, plants, microorganisms, and the atmosphere. Two main types, aquatic and terrestrial, and again, the aquatic systems, which we concentrate on in this talk. We have two main categories, stabilization ponds and constructed wetlands. Again, we concentrate on the second one. We have free water surface and subsurface flow as two main categories of constructed wetlands, and these two, the subsurface flow constructed wetlands, have two subcategories, horizontal and vertical flow constructed wetlands. We see schematically its system. Dr. Vassilios also described them. Free-water surface constructed wetlands are the simplest systems. They are just simple basins containing earth to a depth of about, or a thickness about 50 centimeters, and then water flow, the plants are planted on this earth material, and then wastewater is flowing above in a small layer of thickness of, or a depth of about 20 to 30 centimeters. As wastewater comes into contact with the plants and also the litter material on the bed, then you have there various processes that lead to wastewater treatment. In this case, wastewater is exposed to the atmosphere. In the second case, which is the horizontal surface flow constructed wetland, wastewater flows underground. It flows within a porous media which is contained in the bed and where the plants are planted. And this porous media can be sand, gravel, rock, something that is very, very porous and allows water to go easily through. I believe here, okay. The third type, which is also very common in Europe because it requires less area to construct, is the so-called vertical flow constructed wetland. In this case, we have beds which comprise of several layers of material of different gradation, porous material of different gradation, and we go from top to the bottom, with finer to more coarse material, like sand, fine gravel, medium gravel, and cobbles, as it is shown here. In this case, the wastewater floods the basin, and then it starts percolating like this through the porous media, and it is collected here at the bottom. All these systems can be combined to make hybrid systems consisting of various types of constructed wetlands. And here we see a common type, which has primary treatment first. Primary treatment can be as simple as a coarse grid, or it can be a grid followed by a settling basin, or a grid followed by an anaerobic stabilization pond. And then we have two stages, stage 1, stage 2, of vertical flow constructed wetlands, and then a third stage of horizontal flow systems. Sometimes we also install here at the end a disinfection device. So why using these systems? What are the advantages of these systems? I compare them here in this table with conventional treatment systems, the biological treatment plants. And we have here on the left, we have use of non-renewable energy sources, both in construction. The main materials are concrete and steel, and also in operation, electricity, chemicals, etc. We don't have this type of things in constructed wetlands. We have large quantities of byproducts in conventional systems. For example, sludge. Sludge is a major thing because it adds a lot to the total cost of the operation of the system. We don't have byproducts in constructed wetlands, or the quantities are very small. Actually, most systems have on-site treatment of sludge, as we're going to see. Here we have mechanical parts in conventional systems, and that's a headache because they cause various maintenance problems, or if something breaks, then the facility goes out of operation. And of course, all this means cost. We don't have mechanical parts in constructed wetlands. We have a requirement for specialized personnel to operate the facility on the left. We don't have such requirement here on the right. Actually, in most systems we operate here in Greece, the plumber of the village or the settlement has a small assignment to visit the facility every day and see if it operates well. We have high construction and operation cost here on conventional systems. The construction cost is equivalent or slightly lower for constructed wetlands, but the operation cost is minimal. So here is the big advantage of these systems. But also everything has disadvantages also, and the main disadvantage is the large area demand. Here we have processes in constructed wetlands that follow the rates that would occur in nature. So we have large hydraulic residence times, where here in conventional systems, we have small hydraulic residence times because we accelerate the processes by using electricity and chemicals. So for this reason, these systems, the constructed wetlands, are good for rural communities where there is available land. Here is a conventional system in Paros Island for 5,000 people. You see concrete and steel dominating, and here's the contradiction, stabilization ponds and constructed wetlands. That's from the facilities of the Natural Agricultural Research Foundation in Thessaloniki. Irrigation with wastewater, alternative natural treatment systems here in Heraklion. These are the experiments of Dr. Angelakis down in Crete, where he treats olive meal wastewater with free water surface constructed wetlands. Examples in Europe. Here's a small system in a village in France. It treats wastewater from 250 people. It's a conventional system, as you see here, but the sludge goes to these sludge treatment wetlands. There are specialized systems to treat sludge, and they have solved the problem of sludge. Sludge stays in the system for 4 or 5 years. Then, after this time, it is transported and it can be used in agriculture. Another system in France, 400 people. It's a vertical flow constructed wetland. Here's the coarse grid, which is the pre-treatment for these systems. In France, they introduce both the liquid part and the sludge in the constructed wetland, and the sludge is trained on the top of the system. So it accumulates here and stays there and gets treatment. Another system in France, 1,250 people. You see again the sludge, which is collected on top of the constructed wetland bed. A system in Portugal for 500 people. Here's a horizontal subsurface flow constructed wetland. And also this cell is used for sludge treatment. The sludge is separated in an aerobic pond, and then from time to time it is pumped in the sludge treatment wetland. And a very large system in Portugal, it treats wastewater for 23,000 people. It has a series of various types of natural treatment systems. Here is an aerated pond, a facultative pond, a maturation pond, and constructed wetland, and various gravity filters. So what's the experience in Greece? Most of it comes from our work at Democritus University of Thrace. We have pilot-scale experiments of various designs, monitoring of full-scale facilities. We design systems which have been constructed, are in operation now, and also we developed various models and decision support systems. This is part of open-air laboratory. Here's a series of experiments that's part of the PhD work of Dr. Akratos. He's now a professor at the University of Patras. And the experiments are on pilot-scale units in horizontal subsurface flow constructed wetlands, where he tested the effects of plants or no planting, and the effects of various substrate materials, also the effect of the hydraulic residence time in the system, and the effect of temperature. And some typical results, you see that performances are more than 90% as a mean for BOD removal and COD removal. Also when the the residence time, the hydraulic residence time is short, for example, 6 days, which is shown here, then you get slightly less performance. So 8 days of HRT is enough to have a good system performance. Some other systems, vertical flow constructed wetlands, we have here 10 tanks with parallel experiments in various conditions. And this part of the PhD of Dr. Stefanakis. Now he's a lecturer at Brighton University in England. And we found very good results here for the performance of vertical flow constructed wetlands, which also these results we applied later in designing the various systems. I want to show you how a vertical flow constructed wetland shows again, this from the pilot scale unit. So this is the bed layer, which is coarse. There are aeration devices, these perforated pipes, which go all the way down to the bed, and they communicate with the open atmosphere, and they bring fresh air in the system. So the system has good oxygen conditions, good oxygen concentrations, and therefore it's easier the treatment of organic matter and nitrogen. On top of this coarse layer, you have a finer layer, and then a further finer layer, and then the vegetation, and you also see here the aeration pipes. In these systems, we treated also sludge, and we got also very good results. We got sludge from a nearby biological treatment plant, and at the end of the experiments, we had good mineralization and stabilization of the sludge, which made a very good material to bring to agriculture and use for soil improvement. We also tested the effect of various materials like zeolite and bauxite to be used as for further polishing of the effluent of constructed wetlands. So the experiments, here's the percent removal in the constructed wetland, and then the effluent was introduced into the filters, and we see how much improvement you get when you pass the effluent through these materials. Very good, both bauxite and zeolite remove an additional degree of BOD and COD. Zeolite is very effective in removing additional nitrogen, and bauxite is effective in removing additional phosphorus. Monitoring of full-scale facilities. I'm going to show you here the results on Nea Maditos. That's the constructed wetland we're going to visit on Sunday, and Gomati. These were monitored for more than 2 years. Nea Maditos constructed wetland was designed for 3,000 people. That's a plan view of the facility. We have the entrance work. IMCO tanks are used for primary settling of solids, which are introduced into sludge treatment beds. And then you have 3 stages. We have 3 stages, 1, 2, 3, of vertical flow constructed wetlands. And finally, we have 2 stabilization ponds, which are used for disinfection of the effluent. Here are some use of the system, the inflow works and the IMCO tanks. The sludge treatment basin, you see the sludge flowing here in the basin. This basin was never emptied, so the sludge, the facility operates now for close to 25 years, and there's no sludge removal yet. You see also here the first stage. That's a winter picture, so the plants are dry, but they are dry on the above ground part. The root system still operates in the winter. You see here these devices which are used. They are called siphons, and they are used to feed wastewater from one wetland cell to the other. And the reason of using this device is to instantaneously flood the constructed wetland. In that way, we can use the whole area. You see again the plants here. That's a picture in March, 26th of March. 1 week later, as temperature raises, the plants start getting green, and 4 weeks later, in the same location, they can occupy the whole facility. Also, you see here a view of this facility, Neamatitos facility, as one looks from the downstream end to the entrance works, and obviously it's a very nice picture, which doesn't show that there is a treatment facility here. So from this point of view, the aesthetics, also this wastewater facility, this constructed wetland facilities work very well. Okay, in terms of treatment, you see here main removals. So we have BOD and COD removal that reaches on the average more than 90%. TKN and ammonia nitrogen removal, about 85%. Phosphorus removal, total phosphorus, close to 40%. TSS removal, about 90%. And total coliform removal, close to almost complete removal. The Gomati facility, it's designed for 1,000 people. We have entrance work and settling basins here, and also siphon again. And then the sludge. The sludge treatment basin, and then first and second stages of vertical flow systems, and then a third stage of horizontal subsurface flow constructed wetland. Some use the first stage and the second stage and the third stage of the wetland. And in terms of performance, similar results. I'm going to show them here. BOD-COD, 90%, TKN, ammonia, close to 85%, phosphorus, 60%, total coliforms, close to 100%, and TSS, above 90%. So in terms of design now, we have small-scale systems. So we design these constructed wetland systems for 1 or 2 families, and also we have designed full-scale systems in various villages or cities in northern Greece. Here is one on-site system that serves one family of 4 persons. It comprises 2 settling tanks. One overflows to the second one, and then this overflows to the constructed wetland. This is a horizontal subsurface flow constructed wetland. The thickness is about 50 centimeters, and then the dimensions are 10 meters in length and 2.5 meters in width. So the area is about 25 square meters. Then the effluent goes into a zeolite tank for the polishing step. You see here some views from the construction of these systems. Here are they were made from concrete in this case. Then you place the gravel and then the final planting of the system and the fully operational small constructed wetland. The zeolite tank is here. The winter operation with the vegetation dry. In terms of performance, we monitor the system for about 3 years, and we get the percentage, 90% BOD, TKN 85% on the average, phosphorus 60%, total coliforms close to complete removal. The effluent is used for irrigation, on-site irrigation. Here is the vertical flow on-site system. Again, we have the 2 settling tanks. The effluent goes to a pump station, and then wastewater is pumped to irrigate the top of the vertical flow systems, which comprises 2 cells. And then the effluent from the constructed wetland goes to the zeolite tank here. I show with the mouse, but nothing shows, I guess, all this time. We have here are the 2 settling tanks and the pump, the profile of the constructed wetland. Feeding is from the red pipe on top, and then you also see the aeration pipe to the left of the system, and the zeolite tank to the right. Picture from the construction. In the center picture here, top center picture, you see the piping. The lower pipes are the drainage pipes, which collect the the sewage from the system, and then the top pipes here are the aeration. And down here in the lower pictures, you see the pipes that feed the wastewater on these systems, and also the planting of the system. And how the system looks. In terms of removals, 96%, 94% for BOD, COD, total TKN 91%, ammonia 93%, TP 70%, and so on for the other pollutants as you see. Now a small system for 600 people was designed in near Kastoria, which is in a village near Kastoria. It's called Neosikismos, which is a city on the west part of Greece, close to the Albania border. The winter here is very harsh. Here we see the stream that receives the effluent, the terrain where the system was designed before construction, some design parameters. The total mean flow, daily flow was 90 cubic meters per day, population equivalent 600 people. The system is designed in this cascade way, where the only pump is here at the entrance, which brings the collected wastewater from the sewer up to the first stage of the constructed wetland. Then the first stage goes to a siphon, which feeds the second stage here in the middle, and then the third stage, which is a horizontal subsurface flow constructed wetland. We construct the systems in this cascade way, trying to avoid pumps in between constructed wetland cells. And this is an advantage because, as I said at the beginning, pumps always, regular mechanical, in general mechanical parts create problems of maintenance and cost. This is the plan view of this system. Each stage has different constructed wetland cells. For example, A1, A2, and A3 belong to the first stage, and they are used alternatively. So in a wet and dry cycle. So when A1 is fed, then A2 and A3 rest. They are not fed with wastewater. And so they get an opportunity to receive oxygen and improve oxygen conditions of the substrate. And this cycle changes every 3 to 4 days. So 3 or 4 days we have wet conditions, and 7 or 8 days we have wet conditions. You can skip that. Here's a plan view of the system. The pipes that shown are at the bed, the drainage collection pipes and the aeration pipes, and on top with solid lines are the pipes that feed the wastewater on top of the constructed wetland. A view of the siphon between the cells, percentages similar to the ones I mentioned before in terms of removal. Cost now, about 197,000, including now the engineer's fee and the contractor's fees, and also the taxes, goes up to 286,000. That was the cost of this system. It was constructed a year after design, and this comes down to 477 euro per person served, per population equivalent. Some pictures from the construction, the earthwork and the piping. It's very important to have a specialized team which will install the membrane to avoid, and will glue the membrane. Gluing of the membrane is very important to avoid leakages to groundwater. And after the membrane, then the pipe is placed, both first the drainage pipes and then the aeration pipes, and then the gravel, and then the pipes that feed the wastewater. And here's the final view of the system. Some other system, one in Komara for 800 people. Here we also have pre-treatment in anaerobic stabilization ponds, and the sludge goes to sludge treatment bed up to the upper left of the design of the sketch here. And then we have the stages A1, A1 first stage, B second stage, and see the third stage. Another similar system in Kyprinos, northeast Greece, for 1,200 people, same design concept. A large system in Sapes for 3,640 people. Now we have many basins. Actually, we have two parallel streams in these systems. So we have two anaerobic ponds at the beginning, two sludge treating basins, 12 cells, constructed wetland cells in stage 1, 8 in stage 2, and then 2 horizontal subsurface flow constructed wetlands at the end. Now to summarize all these systems, I show here data from 9 systems with population equivalent from 540 to 3,640 people, areas from 4,000 to 29,000 square meters, or per person land from 7 to about 9 square meter per person equivalent. This is the total land, including area between the various wetland cells. The active land used for treatment is between 2.6 and 4 square meters per person, and the flow rates vary from 80 to 540 cubic meters per day. Construction costs, total construction costs for these systems varied between 280,000 and 1,230,000. This is for the largest system in Sapes for 3,000 people. And of course, as I said, the main advantage of these systems is their operation, the low-cost operation. And you see here the cost of these systems. If I take the figure per capita, is from 6 to 12 euro per capita. So it's about 50 cents to 1 euro each month each person pays for his wastewater to be treated. We also derived some equations which help in predicting the cost, the construction cost, and the area these systems occupy according to size. And with this, we can conclude, based on all this, that these systems are very effective in wastewater treatment. We can use specialized materials like zeolite and bauxite to improve or polish the final effluent. We can also use the system to treat activated sludge, and they're an economic and reliable solution for the small rural communities. Thank you very much.